All right, in this video, I want to talk about another example of a first degree differential equation. I don't want to ruin it too much and tell you what type it is yet, but the idea is that you have a tank filled with salt water, filled with brine, and you have 10 gallons, and there's 5 pounds of salt in there. And so that means that there's about um, a half a pound per gallon of salt. And then what you're going to do is in the top of it, you're going to pour in saltier water that's going to be more concentrated. It'll have 3 pounds of salt per gallon, and it's poured in at a rate of 2 gallons per minute. Water is drained out of the original tank at the same rate of 2 gallons per minute. So there's always 10 gallons of something in the water. And the question is, how does the salt content change over time if you pour in the salty water, but also this um, water with a slightly, it's still brine that's in there originally, but some of it's coming out, and then you're pouring in extra salty water in there. And so you want to know, that kind of complicates it, but you want to know how much salt is there at time t, how much salt is there after 10 minutes, and then what happens long term. So if you were to do this indefinitely, what would happen? So kind of your long-term equilibrium. So we're going to let A be the amount of salt that's in the tank at time t. Notice that we have A of 0 is 5 pounds, because that's how much we said that there's 5 pounds to start with. And what we need to do is come up with a formula for A of t, come up with, once we have the formula, we can answer parts B and C pretty quickly. So the idea is that we want to come up with this formula. And I'm going to think of dA dt as the rate that the amount is changing over time. So this is going to be the amount of salt entering the tank minus the amount leaving. So minus the amount leaving the tank. And this is going to be, let's see, the amount of salt entering the tank is going to be 3 pounds per gallon. So 3 pounds per gallon times, let's see, the water's coming in at a rate of 2 gallons per minute. And then the amount leaving is going to be, well, think about how much is leaving. If you have amount A of salt, it's going to be A pounds per 10 gallons times 2 gallons per minute. And the reason is that the amount of salt that's going to be leaving the tank is actually not fixed. It's going to be proportional to how much salt is in there, because we're assuming that it's continuously stirred and mixed up. And so the more salt you have in the tank, the more is leaving. So it's actually going to be A over 10 pounds per gallon, because that's how much salt is in the tank at any point. Okay. And times that same rate, 2 gallons per minute. And so it works out to, this tells us that dA dt is going to be, this is a 3, by the way, 3 pounds, so LBS. So 3 times 2 is 6 pounds per minute minus, let's see, A times 2 over 10 is A over 5 pounds per minute. And so this is going to give you a first order linear or even separable differential equation. However you want to solve it is totally fine. Let's just make it, what the heck? Let's just make it linear separable. So you can do it either way. So let's multiply both sides by 5. So we end up with 5. Yeah, we'll just do it. I'll break this down into a few steps. So 5 dA dt is equal to 30 minus A. And then let's divide both sides by 30 minus A and then get the 5 over there as well. And so we're going to end up with 1 over 30 minus A dA is equal to 1/5 dt. And you can keep the 5 over. I don't know why I moved the 5 over, but it doesn't matter. And so then we can integrate both sides and we end up with, let's see, negative natural log 30 minus A is equal to 1/5 t plus c. And then we can solve for A. And to do that, we're going to get rid of the negative in front, exponentiate both sides, and go from there. So that tells you that, so this tells you that negative, so the natural log of 30 minus A is going to be negative 1/5 t plus c, again, absorbing the c into the constant, absorbing the negative into the constant, and then exponentiate both sides. So 30 minus a is going to be e to the negative 1/5 t plus c, and that's really just c e to the negative 1/5 t. And then now we can stop messing with the constant. So I guess almost we can stop messing with the constant, but a is going to end up being 30 minus c e to the negative 1/5 t. And we said at the start that a of 0, if you remember, a of 0 was 5. And so that tells you that your c is going to be 25. Okay, and so c is going to be 25. So therefore, your amount that you're going to get, and this is what we're looking for in part A, the amount of salt that's going to be there at any particular point is going to be 30 minus 25 e to the negative 1/5 t. And then if you wanted to compute a of 10, you just take 10 and plug it in. So you're going to get 30 minus 25 e to the negative 2. And so that's going to work out to, when I did this ahead of time, this works out to about 26.6. And then finally, if you think about what's going to happen long term, so for a long-term equilibrium, the limit of a as t goes to infinity is going to be the limit of 30 minus 25 e to the negative 1/5 t as t goes to infinity. And of course, the exponential term is going to go to 0. And so this tells you that long term, we're going to end up with 30 pounds of salt. If we were to do this indefinitely, we will get closer and closer and closer. We would asymptote to 30 pounds of salt in the tank. Okay, but that's the idea. So the equation itself isn't complicated. I just, since we hadn't talked about this, wanted to do an extra video on this example.